I'd like to start the morning's session. Our first speaker is Michael Atiyah of Edinburgh and Cambridge, and he's going to speak on twisted K-theory and physics.
Well, in any serious program, there's usually a light interlude in between so you can recover. And after all the heavy stuff with strings, black holes, deep brains, and so on, this is a light topological interlude before you get back to the serious business. Now, many years ago, about 40 years ago to be precise, I was working on what subsequently called K-theory, and nothing surprised me more than when I discovered many years later that these things were actually useful for physicists. That was very gratifying, particularly since not only were they using the sort of basic K-theory, but they were also using many of the very delicate refinements which we like to introduce. But what was embarrassing is that more recently the physicists have even found uses for theories that we didn't work out. And you'll find in the physics papers references to some new theory, a little bracket saying mathematicians haven't worked this out yet. So that's my reason for looking at this and trying to understand it mathematically after the event, so to speak. So let me first, and this will all be very elementary. If you don't know anything about K-theory, don't worry, it'll all become clear. Now, it all starts off with the question of the quantization of charge, and you know Dirac's famous argument that led to the quantization of electric magnetic charge that says certain real numbers, which actually turn out to be integers, and his argument is well known now to be really a topological argument, which in modern language is concerned with the first Chern class of aligned bundle on the sphere, and so on. And because bundles come into this story, and K-theory is a group made up out of vector bundles, it's not too surprising that when you generalize the original situation of Dirac to a more complicated situation as appears in modern string theory and so on, that K-theory has turned out to be related to questions of charge. Now, for simple cases, K-theory and homology turn out to be essentially equivalent. Over the real numbers, they're always equivalent. But there are some subtleties which distinguish between them, and those subtleties are actually of interest in different physical theories. So various variants of K-theory have been used, and they appear to be what's needed. They give the correct answers, at least they fit the physicist's intuition, and these theories go by different names. There's ordinary K-theory based on complex vector bundles. There's a real or orthogonal theory based on real vector bundles. There's an equivariant theory based on having, a finite symmetry group. And there's another so-called real theory which involves complex conjugation. And you'll find various papers in the physics literature by Moore, Douglas, Witten, and others, which explain the ways in which these different K-theories are related to computing charges in different situations. In addition to these, there are very other ones, and those are what I'm talking about now, which are called twisted theories. These are very analogous to twisted cohomology in classical topology, or what's called homology with local coefficients, but they're more subtle. And this is the one I'm going to explain, and I'll start by reminding you about the situation with ordinary homology. Now, the simplest case, so I can consider, if you have a cohomology with local coefficients on a space, what this means is that you have a space with a fundamental group, pi 1, and some way in which it acts on the coefficient group that you're using for the theory. Now, if you have ordinary integer coefficients, the only automorphisms of the integers as a group is sending 1 to minus 1. And so only the sign action of the fundamental group can be involved, and therefore what you've got is a situation where you have a space X, and you have an element of the first cohomology with Z2 coefficients, which characterizes elements homomorphisms of pi 1 to Z2. And that's the same thing as saying that you have a double covering of X, which you might call X alpha. Alpha is the element of H1 that describes the double covering. An example of that is, of course, if you have a non-orientable manifold, then its orientable double cover is of this form, and the alpha is then called the first Stephen-Whitley class. In this situation, then it's elementary to work out how to define homology or cohomology with twisted coefficients. You use the ordinary description by simplices and triangles and so on, but when you go round, you put in the minus 1 twist. And so if every choice alpha of this element in H1, you get a new cohomology theory, which you could label that way, cohomology with twisted by alpha. Now, another way to describe that, or equivalent, is to say the following. remembering that Z2 is the same thing as the orthogonal group in one variable, you can take the real line bundle, which is determined by this double covering. In other words, as you go round a loop, the line simply gets reflected if you go down the basic loop. So if you call it L alpha, the real line bundle determined by alpha, then the following is easy to see, that the twisted cohomology of X for alpha in dimension Q is the same as the cohomology of the space L alpha in dimension Q plus 1, where this is interpreted as cohomology with compact supports. In other words, you work modulo things at infinity. The 1 is because you're going up in the dimension. If alpha was 0, this would just say the cohomology in dimension Q of X is the same as the cohomology in dimension Q plus 1 of X times a line. But the twist here corresponds to the twist there. This is ordinary cohomology of a twisted space. This is twisted cohomology of an ordinary space. And they're the same. And this is actually what you might call the twisted suspension isomorphism. A suspension isomorphism in the usual situation when there's no twist. And it's also related to Poincare duality for non-orientable manifolds. If you have a non-orientable manifold, then Poincare duality relates one's cohomology with a twisted version. So this is just reminding you of very classical topology, what you mean by cohomology with twisted coefficients. Now, by analogy, we could, of course, then take this as a hint to define the K-theory of twisted coefficients in exactly the same way. We could define the K-theory in dimension Q. Q in K-theory is periodic with period 2, they're just 0 and 1. And the K-theory twisted by alpha, you could define exactly the same way as before, as the K in Q plus 1 of this twisted space with compact supports. That's obviously a very natural thing to do. Now, if you could, this space here can be fitted into an exact sequence or an exact triangle. When you have a periodic theory, instead of writing line long exact sequences, it's convenient to put them into a triangle. You can just go around the triangle once, and then you shift by 1, you go around again, and you've got the whole story. And so if you consider the pair of spaces, which is the unit interval part of the line bundle, which I call I alpha, and the boundary part, which is the two endpoints, which is the double covering X alpha, this pair of spaces, as usual, applied to any theory, gives rise to a exact sequence. And this exact sequence you get here is applying it to that. This bit here is, by definition, that, which is the same as the relative group. This is the one space, and this is the other space. And this exact triangle follows by applying K-theory to this pair. And what we've got here, this is the ordinary K-theory of the, remember, X is the base space, X alpha is the covering space. So the map X alpha projects onto X, so you have a pullback. That's the natural pullback. And you can say that this one is defined in order to make this triangle exact. So once you've got these two, this is more or less a fourth definition of the twisted version. Now, that part of the story, so far I've talked about a space with a double covering, or other way around, if you start with the double covering, you have an action of Z2 on it, but this action is free. It has no fixed points. Now we generalize that to the case where the action may have fixed points. So, not to confuse you, I will call the space Y. So Y is now, would have been X alpha, but it now can have fixed points. And because of this exact sequence there, and because the following is obviously true, that if you have a space in which the action is free, like on X alpha, the action is free, the equivariant K-theory of this is the same theory as the K-theory of the quotient space. There's no fixed points, that's rather tautology almost. So you can rewrite this bit here in general in terms of the this sequence here suggests this following one here in general for fixed points. Maybe you take the equivariant K-theory of a space with an action of Z2, and you map it to the ordinary K-theory by forgetting about the action. That's this map here. And then you try to define the third one to fit into the exact triangle that would generalize this one. So that's, in other words, if you want to go away from allow fixed points, we want to find the definition of this group. And this is the group that has appeared in physics. This is the one I want to talk about, and I want to tell you several things about it. Now, so this is our background, how one might have got there with hindsight. Now, it's always true that if you have a two-point space, there's 2 points, and you have an involution on the space, and you make it act by acting here and interchanging those 2 points, then trivially, the equivariant K-theory of this is just the ordinary K-theory of one copy. These are 2 copies, this is 1 copy. And so if you apply the equivariant K-theory to a pair of things like this, then you'll get an exact triangle, and that exact triangle is the one we had before, and this relative group you're trying to define, if you follow it through, comes out to be this thing here, namely this k plus or minus appears to be equivariant K theory with a shift in index applied to y, the space, times the real line, where this is interpreted as the K theory with compact supports, and the involution acts on y as given and acts on the real line by reflection. And this star is the definition proposed by Mike Hopkins, because these groups were introduced by Edward Witten as a natural home for charges in connection with orientifolds. So in this analysis of what charges arise in different situations, he discovered that for orientifolds you needed a new kind of K theory, and he gave this label, K plus or minus. The plus or minus has to do with an ambiguity. You don't know whether you're talking about plus or minus, and so, not a bad notation, I copied it. And then he asked Mike Hopkins, what is this object? And Mike Hopkins went away and thought for a while and said, well, the best he could come up was this was the definition. Maybe his motivation may not have been the one I've given here, but and with this working definition, it seemed to fit the facts, and so this has been adopted as the definition which is then computed with. Now, a couple of comments about this definition is, first of all, if the action is free for no fixed points, then we recover what I started with at the beginning, what I call the twisted K theory, and that's actually been known for a long time before. The other extreme is when the action is completely trivial, when the whole space is fixed by the space. In that case, it's very easy to see that what you define this way is actually the ordinary K theory shifted by 1. And that you can see by writing down the exact sequence and observing that the equivariant K theory are, when this action is trivial, is just the product of the ordinary K theory and the representations of the group. And the group, Z2 has two representations, so you get two copies here, and one copy is killed there, the other copy survives there with a change of index. So this is an easy consequence of the definition, and this is good. I put the blue arrow because this fits in with the physics intuition in the relationship between type 2a and type 2b, as I understand it. So physicists are happy with this one, and they're happy with the others, so this has been accepted as the good definition for physics. Now, K theory has a different incarnation, which is important for physics, because it involves analysis. It involves operator theory. It involves in particular the Dirac operators and their spectral properties. So it's very useful to have an alternative approach to K theories, which makes transparent the relationship with things like the Dirac operator. So that's what I want to talk about now. So let me start with a little background, elementary Hilbert space analysis. If you have Hilbert space, then you can consider bounded operators on Hilbert space, and an operator is called a Fredholm operator if it has a finite dimensional kernel or null space, and if the adjoint operator also has a finite dimensional null space. And if you call these dimensions p and q, then the index of the operator is called p minus q, and it's an important property that it is invariant under deformation, under continuous variation. This does not change. P and q can jump, but they jump in such a way that they cancel. So if you denote by curly f the space of all Fredholm operators, it has a natural topology given by the norm of an operator. You can do the following thing additionally. You can study not a single operator, but you can study a family of operators parameterized by some parameter space. So a continuous map from some arbitrary space x into this big space f is simply a family of operators parameterized by x. And then you can define the index of this family not as an integer, but an element of k of the parameter space. And the naive idea is simply the following, that for every point little x in big X, you consider the operator you get from that. That has a kernel and a co-kernel, or kernel of the operator and kernel of the adjoint. As you move around, these vector spaces will vary. If you're lucky, they may not change in dimension. Then they will form vector bundles. Then you get one vector bundle here, another vector bundle there. You take their difference, because K theory is precisely manufactured so you can do that, and you get an element in K theory. Now, if of course you're unlucky, the dimensions do jump, and that can be typical, but in fact it turns out you can always modify the situation such a way that there are no jumps, and show that the answer is independent of the way you modify it. So it is in fact true that any family of Fredholm operators has an index in the K group of the parameter space. Not only that, but this is a complete classification of all the topological information in here. If you consider the note by square brackets x curly f, the space of all maps up to homotopy equivalence, then that is isomorphic to K of X. K of X can be thought of, or defined if you like, as simply the homotopy classes of maps into Fredholm operators. It shows that the index, in this generalized sense, contains all the topological information about the way the operators vary. So that really explains, from another point of view, why K of X is rather naturally associated to the study of Fredholm operators. Now, of course, in physics, the natural operator to consider here is the Dirac operator. So let me remind you, if you have a compact manifold which is spin, and let's say of even dimension, then you can form the spinners, and they can form into two types, which you call plus and minus, and there is the Dirac operator which goes from one to the other, and the other one going backwards is the adjoint of the first one, and the index of the Dirac operator is then the number of zero modes of this one minus the number of zero modes of that one. Now, technically, of course, a differential operator is not bounded, but that's a minor technicality. If you take a differential operator and you divide it by the square root of 1 plus d star d, this is a positive Selfadjoint operator, it has a square root, then this has degree 1, and degree 1 cancels, operators of degree 0 are bounded, so this is the bounded operator, and it's easy to see that this bounded operator and the Dirac operator have the same set of solutions. So forget about the technicality that these are not bounded operators. The Dirac operator essentially is a Fredholm operator, and therefore the index of the Dirac operator is what we've been talking about. And therefore, if you have a geometrical situation where, for example, you have a family, a fibration of a space manifold Y over a manifold X, then and if the fibers are compact spin manifolds of even dimension, then for every point little x in the base, you have exactly the situation of a Dirac operator. And the Dirac operator may be a pure spinors, or it may be coupled to an extra vector bundle. Then you can take the index, that's an operator, which is Fredholm. As you vary the point x, you have a family of Fredholm operators. And therefore, you have an index in the K theory of the base. So here is the geometrical situation where you see that if you have a fibration and the fibers are spin, you automatically get an element of K theory in the base arising out of the study, really, of the spectral properties of the Dirac operators in the vertical directions. So that's the fundamental link between the K theory and the Dirac operator. Now, I mentioned at the beginning there are refinements, and so the simplest refinements are that you can consider, for example, real operators. Then you get real K theory, nothing changes, the story is the same. Equivariant theory is more or less the same too. Take any finite group or even a compact group, then you can consider the situation where that acts on the space X, and you take a Hilbert space which involves also the group, for example, the Hilbert space times the regular representation of the group. So the group acts on both sides, and you just plug everything in, and these are maps compatible with the G action. This is equivariant K theory, which I haven't defined, but you can define easily, made from vector bundles together with geometrical action, and the statement is still true. So all these, what I said before, extends with practically no change to these generalized cases. And this equivariant case, by the way, is the K group that is relevant, if G is a finite group, is relevant for orbifolds. Now, with all this background, we can return to our particular examples of these twisted K theory, and we ask ourselves, is there a definition of Fredholm operators which is related to this K plus or minus? So now you start make the following observation, that given any Fredholm operator, we have its adjoint. And that defines an involution, or action of the group Z2, on the space of Fredholm operators. And if you consider the maps of X into F as giving you the elements of K of X, it's easy to see that this involution on the space F, what it induces on K of X is simply -1, because you see, taking the operator to its adjoint, interchanges the roles of the operator and adjoint, and the index with the difference of the two, so when you switch them out, you get a minus sign. So this is the natural involution, it gives you -1. And now, if now you go back to the case of a covering space, a space with a double covering, you can see that you can form, a natural way, a bundle over the space X, whose fiber are Fredholm operators. Every time you go around the loop which picks up a minus sign, you identify the Fredholm operators at the beginning with those at the end by using the adjoint. You flip it over. You get a kind of twisted family of Fredholm operators, which you might call F suffix alpha. And now you can then define, you see, or prove that the twisted K theory, K0 of alpha of X, is actually the homotopy class of continuous sections of this fibration. A section of fibration is just really like a twisted map. If the fibration is trivial, it's just a map. So if the fibration is not trivial, it's a twisted map. And so the twisted maps correspond to the equivariant K-theory. So here we have a very simple generalization of the interpretation of K-theory involving Fredholm operators to the twisted case. And this is rather simple to see in terms of the previous definition. And now this question is, I want to go on to consider the case where the involution acts with fixed points. So this suggests, at least, that for a general case, you could either define the k plus or minus of y as the equivariant maps of y into space of Fredholm operators, where the z2 action on y is the one that's given, and the z2 action on f is given by the adjoint. If the action is free, it's easy to see that this is the same as that. A section of a twisted bundle is nothing else than an equivariant map of the double covering into the Fredholm space f. So this is a naturally reasonable guess from that one. So let's see whether that stands up to closer examination. So the other extreme case, besides the case of the free action, is the case of the trivial action. So you ask yourself, what happens for a trivial action? Well, for a trivial action, of course, then if the z2 acts trivially on y, it must map into the fixed points of the z2 action on the other side. The fixed points of the action sends an operator to its adjoint is precisely the space of self-adjoint operators. So let's denote by f the hat on it the space of self-adjoint operators. Now this thing here should now be the maps of y into self-adjoint operators. Well, fortunately, the topology of the space of self-adjoint operators was studied a long time ago as well. And here is the basic facts that this space actually has three components. Two of them are interesting. An operator may be such that it's essentially positive. Almost all its eigenvalues with finitely many are positive, or essentially negative. And either of these are not interesting, because in the positive case you can push all the eigenvalues away to plus infinity, if you like, and the negative one you push them all the way to minus infinity. But there's the interesting cases where they straddle across. And you can't push infinitely many eigenvalues across zero. That would contradict the Fredholm assumption. This is the interesting part. You throw away these other two, and then there's the theorem, which Singer and I put a long time ago, that the maps of a space into the self-adjoint ones, the essential ones, gives you K1. For example, if y is a circle, then this gives you what's called the spectral flow, or the spectrum around the circle. This it then checks with the physics, remember, if we throw away these two. Well, there's a minor technicality of how you do that, and I may not have time to do that, but since I've only got the orange light and not the red light yet, I can put it up for you. What you do is you stabilize the problem by enlarging your Hilbert space. You double it up, and you have your original operator in one corner, and you put a fixed operator here, which has infinitely many eigenvalues, plus 1 and minus 1. That guarantees you're always an instant component, and with that definition, the theorem is essentially correct. So that's not an important observation. Now, the interesting thing I would like to finish off with, though, is very quickly, that how is this related to the Fredholm operators? And the answer is that basically the Hopkins definition can be reformulated like this, that this K0 can be written as K0 of y cross R2, where R2, I put index 1, 1, meaning the Z2 has a 1 plus sign and 1 minus sign in its action. And now if you have this situation here, this is really can be compactified to a sphere, with the reflection being the involution. And then the important thing is that the map you want to construct here, which relates the first definition to the second definition, should be got by using the Dirac operator on the 2-sphere. That's a family of operators, and it will give you the right answer because the reflection changes the orientation and precisely replaces the Dirac operator on the sphere by its adjoint. Therefore, this Dirac operator family is the natural map between the two candidate definitions I gave you. In the case, by the way, when you have this orientation preserving map, this is usually related to the Bott periodicity theorem, and the important thing is that on the 2-sphere, the Dirac operator has different properties depending, of course, on whether you apply a Z2 that preserves the orientation or reverses it. Now, I've only still got the orange light, so it looks like the chairman's allowing me another minute. Now, this what I talk about twisted K-theory is actually the first level. There are higher levels of twisted K-theory. This first one twists by an element of H1. There's an interesting twist by elements of H3. These are of interest in physics because they're related to the 3-form field H. And this has been much studied, and in fact you should combine that one with the previous one. And the equivariant version of that's also been studied. And there's a beautiful result of Fried, Hopkins, and Telemann that relates this with the Verlinde algebra. I haven't got time to explain that, and I haven't even got time to tell you about the last one, which is that actually there are bigger twists. Which the situation is this: that K-theory, the twists should correspond to elements in the multiplicative group of units of K-theory. The first bit comes from plus or minus 1. That gives you the first twist I talked about. The next comes from H2, the line bundles, That gives you the element of H3 here, which is the one I just talked about. But they actually have a much bigger twist that comes from the highly non-abelian part of K-theory. And these big twists, which have been suggested by Hopkins and Morava, have yet to be studied either by mathematicians or physicists, and so I just leave it an open question as to whether there are any physical applications of these really big twists. This might be a case where we're ahead of the physics. So far we've been behind. Well, I'll stop there.
You've set a wonderful standard for all of the further speakers today, both in the quality of the talk and the attention to the lights in front of you. Surely there must be some questions. Edward.
Ed Witten from the Institute in Princeton. So can you give us a hint about what some of these big twists are?
Well, I mean, the first few are twists by elements which come from ordinary cohomology, of course. The other ones are twists by elements that come internally in K-theory. And I think, although there's some vague ideas as how you might interpret them in terms of functional analysis, nothing really has got off the ground. So, I mean, it's very early days, and maybe you're of no interest. And the difficulty is, I think, with any definition you give in mathematics, you can give a definition, but the question is, are there examples? I like to quote this statement of Prospero, in Shakespeare's play, who says that somebody says, I can call spirits from the vasty deep. And the man says, yes, but when you call, do they come? So I don't know whether this theory, and of course the interesting thing about the ones from H3 is they do arise in physics. There is some interesting story in relation with infinite dimensional spaces coming from fermions and tied up with Kac-Moody algebra and so on. These higher ones, yet we don't know of any examples, either in physics or in mathematics, but that doesn't mean that they don't exist. They might have something to do with higher dimensions than 3. And obviously the first one has to do with dimension 1, and 2, and 3, and 4. This one has to do with dimensions 5, 7, 8, higher up. So the twists, if they exist, have to do with higher dimensional cohomology and K-theory in higher dimensions, and they may be of interest if physicists really aren't satisfied with what they've got and need to climb up into even more dimensions.
I am Raghvacharlu from India. I very much fascinated by what you have been telling, and there is a connection between fundamental physics and profound mathematics. And as I see that many people have been so far mathematicians, they take any idea of physics and they make it very profoundly great, and another physicist comes and gives another idea and it is made profound, and so on and so forth, like that in mathematical domain. Whereas it is, on the other hand, you are from the other side, in the sense that you would like to take an idea of, say, the Dirac operator, and have been seeing the wonderful things which you have been doing with respect to the Dirac operator. You say the mystery of reality is embedded in this one.
Yeah,
Sir,
finish the question for me.
Now comes my question. Is the role of mathematicians always to say that something that appears to be fundamental in mathematics is also of great fundamental importance in physics? Or shall we tell, finally, this way I put my question, are the foundations of mathematics and physics are going to be identical, or as Dirac was telling from the beginning, they should be distinct?
Well, thank you for asking that question. I mean, one I spent much of my time thinking about, the relationship of mathematics and physics. If a good piece of mathematics, should it always have an application in physics? Should it have one? Should it have many? And a good piece of physics, should it have implications in mathematics? Well, that's an open-ended question that keeps us all busy. And on the whole, I'm optimistic.
On that note.